All right, so a few things to do today. First of all, we have a couple of problem sets. We have a chapter 5 problem set, which is based on trigonometry. And then we have a chapter 11 problem set. It's basically in reference to the first half of the chapter that we did last week, which is to say combinations, permutations, arrangements, all that fun stuff, plus sequences. The rest we haven't quite gotten to yet. There is a second problem set that we can either do next week or possibly start it later on today. And then next week, of course, we'll be working on the sampled final. So today's the 5th. So our last meeting is next Wednesday, the 12th. And so then the final exam period begins. And so first things first, let's take a look at Moodle. And let's see. What are we looking for? Yes, the problem sets are here. Yes, let's take a look. All right, so as far as the problem sets are concerned, 5 is here somewhere. Yes, there it is. There's two looks like I haven't posted the second problem set for 11 yet. Maybe I'll just do that right now, just to make sure it's there. And then the only thing that's also missing, the actual sample final, which I'm still working on. I'll have that ready maybe today or tomorrow. And so that way, because of course, we'll be working on that next week. So, here we go. All right, so that's where we're going. And if you look in your Moodle accounts in the grade book, you'll see your grades are in there from the midterm. And if there was an issue where I couldn't find your exam, or if I couldn't read it, there's not going to be a grade there. But there's only 1 or 2 people who fell into that category. Everybody else, you should see a grade there. So in the meantime, let's get back to these problem sets. For example, number 5. All right, now these are pretty straightforward. You're just being asked to calculate or convert angles into each other. All right, so now if you recall, let's go back to the chapter for a second. We introduced the unit circle as a way of calculating trig functions for the standard angles like 30, 60, 90, etc. If you have something else, then you have to do some algebra. But if you look very carefully at this unit circle diagram, which we went through in very great detail last week, a lot of them are listed here. So just don't forget, now the way this works is that if you're using this chart, in each case, each of these ordered pairs, the first number is the cosine of that angle, the second number is the sine. So for example, 60 degrees, or equivalently pi over 3 radians, the cosine is 1/2, the sine is radical 3 over 2. And if you prefer a chart to this graph, there's that too in here somewhere. I've also added a chart, so you can look these up. And so let's see where it is. Up here it is. Yes. So this chart is available to you as well. And in fact, the nice thing about this chart is that unlike this unit circle, this is only showing sines and cosines. The others, you have to figure them out yourself algebraically from the relationships that we established between sines, cosines, and all the rest. For example, the tangent, as you might recall, is the sine over the cosine. The cotangent is the opposite. So this chart, though, down here, does include all 6 of the standard trig functions. And so that might be a little easier to work with. But even here, you might have to do some algebra. If, for example, you're being confronted with an angle like, I don't know, 180 or 360, then you might have to look at the circle. But anyway you look at it, it shouldn't be a problem. Now, if you have the right calculator, if you have, let's say, one of the Texas Instruments calculators, you can calculate these directly. And if not, most likely, although I don't know myself where they are, let's take a look at Symbolab for a second. It may have some of this as well. Our old friend Symbolab, which we haven't used in a while, could be very helpful for something like this. Let's see how they are with their trig functions. For example, what if I want to know the sine of 90? All right, so what happened here? It says here the sine of 90 is 1. Is that what my chart says? Well, let's look over here. 90 degrees is here. Yeah, the sine is 1. Remember, in these ordered pairs, we always have the cosine first and the sine second. So far, so good. All right, let's try one of the more obscure ones. Let's try from my chart. Let's say cotangent. Oh, how about cotangent 45 degrees? But let's call it pi over 4. All right. Whoops. No, that's pi over 2. Let's change that to pi over 4 and see how it reacts to that. It says it's 1, and that is indeed the case. Okay. So it looks like this thing is probably reliable. Now, here's the only problem, though. Let's try one of the ones that turns out to be a radical. Like, let's do the sine of 60. All right. I just want to see what it does with the fractional ones. Oh, okay. It is radical 3 over 2. I was going to say, you might not recognize 0.866 as radical 3 over 2, but it's very kindly doing them both for us. So that's good to know. All right. So don't forget about this little secret. So if you find yourself having to do trig functions on the final exam, well, here you go. Here's a very helpful tool. But if not, you can still use this chart or, of course, the unit circle. Of course, we saw with the unit circle how all these angles are derived, not the angles, sorry, the cosines and sines, and then we can do the rest. All right, so that being the case, let's take a look at this chapter 5 problem set. So now here, I don't know if Symbolab can help us with this. It's asking us to convert radians into angles. Now, how exactly do you do that? All right, well, it's actually pretty straightforward. All you need to do is multiply by 180. Let's do that right here. You can see what's going on. So you'll take 180 times 3 pi over 4. And so what happens is you don't actually need the pi then. Here's what you're going to do. Multiply this by 3/4, and you'll get 135 degrees. Okay, because remember, pi radians equals 180 degrees. That's the key to the whole thing right here. So I'll make a little note here in the answers. Pi radians is 180 degrees. So basically, you're making a substitution here. The pi is being replaced by 180. And so 3/4 pi radians is 135 degrees. Now, if you're not sure, let's go back and look at our unit circle. All right, so we're looking at, let's see. Let's get these lined up. So if you look at the circle, there it is right there. 3/4 pi is equivalent to 135 degrees. And that's the reason why. So once you know the secret, it's easy. You're literally just replacing the pi with 180 degrees. And that will give you your answer. And if you're not sure, go ahead, double check, and you'll see that in each of these cases, that's exactly what they've done. So here, for example, you'll have 180 over 9. It's 20 degrees. Now, that angle may not be on here, by the way. They're not all here. Pi over 9, let's see. No, that one slipped through the cracks, but that's okay. We know what's going on here now. Just like this one, minus. Now something like this. Well, let's do it the way we've been doing it. Minus 5/4 times 180 is actually minus 225 degrees, which is fine. But we usually try to express angles as a positive number. So if we look at this unit circle, minus 225. Now you see what they've done here is they've left off the negatives. So we'll have to do this ourselves. So here's how this works again. So what does negative mean? Okay, negative means you're going in a clockwise direction. Okay, so let's see. So this angle that I'm drawing here is a total of 225 because it's 45 here. And of course, this semicircle is 180 degrees. So altogether, this is negative 225 because we're going in a clockwise direction. The equivalent angle, the equivalent positive angle means we're going in a counterclockwise direction. So you can see this time I'm going 90 degrees plus 45. So that means this is equal to positive 135. So mostly what we should probably do is stick with the positive angles. Okay, so in other words, yes, technically negative 225 is the correct answer, but under normal conditions, we try to stick with the positive angles. So what we might want to do here is call it 135, even though I wouldn't take points off on a test if you called it negative 225, but just be aware that normally we try to express all angles as positive numbers. Okay, and then finally here we just have 180 over 3, which is 60 degrees. This one's probably on the unit circle diagram. Let's see, pi over 3 is right here. Yes, 60 degrees, perfect. All right, so that wasn't too painful. Oh, yeah, I'll probably do that tonight. It isn't quite ready yet, but it'll be very, or maybe actually, yeah, I mean, the thing is, we haven't done the sample final yet, but if you want to start early, that's okay. It isn't quite ready yet, but it should be ready in the next couple of days. So if you want, I can just post it as soon as it's ready rather than waiting till next Wednesday. No matter what happens, though, you'll have at least a week after next Wednesday's class because next Wednesday is the last day of classes. So no matter what happens, you'll have a minimum of a week to get it done. Okay, just be aware of that. But if you want, I can post it as soon as it's ready, which probably will be the next couple of days. All right, anyway, so those are done. So now we're going the opposite direction. We're going from angles to radians. So now our strategy is to do the opposite. Okay, so let's get these set up. Okay, so what that means then is that what we have to do is divide by 180 pi. Sorry, 180, divide by 180 and multiply by pi. All right, and this is the reason again why, because pi radians equals 180. To convert this, that means that 1 degree equals 1 over 180 radians. No, not 1, pi over 180 radians. That's the logic right here behind what we're doing. So therefore, what I'm actually doing here is multiplying this by pi over 180. In fact, why don't we do it this way? Let's use our 90 and multiply it by pi over 180. I think this way it'll be more clear what we're doing. Okay, so therefore, it should be pretty clear that in this case, you're going to wind up with pi over 2. Okay, so again, this is the reason. If pi radians equals 180 degrees, 1 degree must be pi over 180 radians. So I take any angle that I have and multiply it by pi over 180, and I'll end up with the correct value. And again, we can double check this with our unit circle. 90 degrees and pi over 2 right here on the top are the same. So down here, I'll take my 180, and once again, I'll multiply it by pi over 180. Okay, oh, that's an easy one. It'll just end up being pi radians. How do you like that? That should come as a surprise to no one, because we just got through saying up here that pi radians is 180 degrees. Okay, so therefore 180 degrees equals pi radians. And again, you can check here, and it's right there. Okay, negative 90, yes. Now negative 90, we can leave it as negative for the time being. But yeah, I guess we can do that. But I think it might be easier, once again, because it's a negative angle, to convert it to a positive angle. I don't know. It just seems like positive angles are easier to visualize. Negative 90 means you're going this way. Okay, so in other words, you're going clockwise 90. This is negative 90. So going this way to come to the same point means you're going 270, because this is 180 and this is 90. So therefore, the total here is 270. So let's convert this to 270 and multiply that by pi over 180. Okay. And so 270 over 180 turns out to be 3 pi over 2. Okay, 3 pi over 2. And again, why don't we confirm that on our unit circle? So we're looking for a 270 right down here, which equals 3 pi over 2, yes. Okay, perfect. And so now, all of a sudden, look what that means. This one is the same. How do you like that? So those are done. We don't have to do them again. All right, now what about these? All right, well, you've got a few options here. You can go right to Symbolab. You can use the unit circle. You can use one of the charts. So let's try Symbolab. Or like I said, if you've got one of the calculators, the Texas Instruments series, it does have trig functions built into it. I don't think the iPhone has that. If you're using the iPhone as your as your calculator, I'm going to look. I don't think they're there. Yeah, no, they. Oh my God, they're down there. Well, I'm surprised as can be. Let's see. Does it have pi? It has a rad button. I'm interpreting that to mean radians. Let's try this for a second. What if I put Huh. Wow. All right, let's try this. Now, pi over 6 would be 30 degrees. Okay. So I'm going to try this on the iPhone calculator. Oh, no, bad luck. It doesn't seem to be working. I don't know. Something's not quite right here. All right, I'll tell you what. Let's not do that. Let's do pi over 6. Let's see how it reacts to that. All right, so pi, it does have a pi button, by the way, in the sort of in the middle towards the bottom. Pi divided by 6. I calculated that or put that in the calculator, and then I hit the, oh my God, it works. So even if you don't have a fancy calculator, I'm sure you have an iPhone, and you probably are aware that it has a really nice scientific calculator built into it. If you go to the calculator app, you have to turn it on its side though to get it into the scientific mode. Okay, so in fact, let me just quickly show you what I'm referring to here. So you go to your calculator, sorry, your phone. You know what this thing looks like, all right? And it's so hard to see because of the glare, but right there's your little. Now, you notice that here's a standard, very crude, basic calculator, but look what happens. Whoa. Nice. That's a serious calculator. So the trig functions are in the bottom left-hand corner, as is the pi. And so if you don't want to mess around with the unit circle, you can do this. Put pi, hit the pi key. Pi. Oh, that's not what I wanted. All right, so hit the pi key and then divide. Use the division. Now, oh, you know what, that reminds me. That symbol for division does not actually appear on our computer keyboards any longer because nobody uses it anymore unless it's a calculator. So the symbol, that thing, yeah, OOF7, okay. There we go. Our old friend division from elementary school. Then put 6, then hit the equal button. And now it'll be something like 0.55 something or other. Now hit the sign button. And there it goes, 0.5. Okay, so you're going to type pi divided by 6 equals, then take the sign, and you'll have your answer. It's so simple. I had no idea that that was even there because, you know, I don't use this calculator. I have the Texas Instruments series, but in most of my classes, people are using this calculator. So whenever possible, I like to show everyone how to use it for all these different purposes. So then that means for this one, oh, and of course, you maybe, you know, as a precaution, you should double check with your unit circle. I'm sure pi over 6 is here somewhere. Yes, 30 degrees right there. Okay, very good. Now let's try this one, divided by 3. Let's see what happens. Pi divided by 3 equals sine. See, now there's the rub though. It's going to come back as 866 something. So for these cases, you may want to, I mean, it's not that it's wrong, but if you look here on the unit circle, you'll see that pi over 3 is actually the sign that is radical 3 over 2. Okay, so this is really the equivalent of radical 3 over 2. Okay. I don't know if there's a way you can convert this 866 back into a radical like this. I don't think so. Now, of course, we still have the option of Symbolab. Don't forget about Symbolab, because Symbolab actually will leave it in that form. Oh God, what happened to it? All right, I don't know how this keeps happening. I just keep losing all these open. I've got so many websites. When I need them, where are they? It's just gone. I don't know how this happens, but all right, let's go back to Symbolab. So we're looking for pi over 3. So I'll choose this one, but change it to 3. All right, well, I just keep typing wrong. Just to confirm. Yeah, there it is, radical 3 over 2, which is decimal 0.86602. All right, now, here's where it gets a little more interesting. Cosine. Well, no, not necessarily. Let's just try these. Because the calculator that you have does also include the cosine. So we'll have pi divided by 6, but then you'll type the number, the cosine function of pi divided by 6 cosine. All right, well, let's see what that is. Oh, it's the same. Well, what do you know? What an amazing coincidence, but it's true. Okay, so we can confirm it in 2 different ways. We can go back to our unit circle, or let's just do cosine pi over 6. Okay. Well, that's weird. I don't think it understands what I want. I don't know what that was all about. I think it was very confused about what I was asking for. I didn't know that could happen. I also noticed that even though when I asked for the trig functions, they seem to have all disappeared here. I don't know what's going on with that. But anyway, yes, it confirms what we said, radical 3 over 2. Okay. And then finally, we have cosine pi over 3. All right, so it'll be exactly the same, except we're dividing by 3. And so this time, what do we get? A half. Oh, I like it when it turns out nicely like that. A half. What did I do? Okay, and so once again, why don't we confirm it on Symbolab? Cosine pi over 3. And yes, a half. Okay, good. Beautiful. So those are done. Now, reference, what does that even mean, a reference angle? The reference angle, remember, is the smallest angle equivalent to this one, which is less than 90. All right, now that you know that there's many different equivalent angles that we can create. This usually involves functions of 180 degrees or so, but you never know. So for example, 90 degrees means Well, that one, I think that that one stays the same because 90 is right here. I don't think there's any way to simplify 90 degrees. But let's just check something out for a second. See, I don't know what that is. So the cosine of 90 is 0. The cosine of 0 is 1. Okay, so you can confirm, in this case, the reference angle is 90 because you can't make it any smaller without changing it. Oh, that's okay. I was just telling them we're doing chapter 5 problem set, the first chapter 11 problem set, and then we're going to finish chapter 11. All right. So anyway, as I was starting to say, the whole purpose of the reference angle is that you're finding another equivalent angle that is less than 90 degrees. Okay. So here the reference angle just is 90 degrees. But if you try 240, for example, 240, what is 240? Let's try a graph. Okay, so this is 240. But the point of this is that 240 represents 60 degrees in the third quadrant. So the reference angle is therefore 60. Okay, in other words, it's trying to get at the idea that we want to stay in the first quadrant. So we want to know the equivalent angle in the first quadrant that equals what we have. Because what you've done here is subtracted 180. All right. Okay, so how does this help us? Well, let's try an experiment here. We've got 60 and we've got 240. So if you read across, what this is telling us, and I don't know if you consider this to be useful or not, but if you look at 60 and 240, if you look at the values of the cosine and the sine, they're the same numbers, but with different signs. So in other words, if this is a half, the cosine, this is telling me the cosine of 60 is a half. Because 240 and 60 are reference angles of each other, that implies that the cosine of 240 must be negative a half because that angle is in the third quadrant where both x and y are negative. Same thing up here with the sine. The sine of 60 is radical 3 over 2, which implies that down here in this ballpark, the sine of 240, because it's in the third quadrant, would be negative radical 3 over 2. So basically the purpose of this, and this is going back to the days before we had computers, is that in principle, if you know the angles, or I should say the sines and cosines in the first quadrant, You don't really need the rest of the unit circle because you can figure out what they would be in the other quadrants by knowing the signs. All right, now at this point in time, what's the big deal? We'll type them both into Symbolab and get our answers. But this was potentially very helpful at a time when, again, there were no computers. So the ones that are facing each other in the different quadrants are only going to have different signs. The numbers will always be the same. So that's really what the logic of this is. And so here I've obtained it by taking away or subtracting 180 degrees, because what I want to do is move this to the equivalent angle in the first quadrant. And once I have that, then I know the relationship between all the trig functions on those two angles. They'll all be the same except for the signs. Okay. So anyway, for the rest of these, now that we've seen what this is all about, negative 170. Now, I don't know about you, but I find negative angles to be a major annoyance. I always convert them back into positives. So again, how do you do that? Well, you can draw a picture. What I would like to remind you that is a shortcut, when you have a negative angle like that, well, let's just do a test. Let's take a look at negative 170. Okay, which means you're moving in this direction. -90 degrees followed by 80 degrees brings us down to negative 170. That implies that this is 10 degrees. And so if I come around on this side, this is 180. This is positive 190. If you're not sure, just note that except for the signs, these two add up to 360 degrees. All right, that's to me a quick and easy way to remind yourself how this works. Okay, if you notice, if I add these up, except for the sign, the two of them do add up to 360 degrees because they represent the same location in the circle. Okay, they're both at the same spot. It's just that in one case we arrive from the counterclockwise direction, the positive number. The negative number represents arriving there from the clockwise direction. So that means I can take this one and immediately confirm or transform it into 190 degrees. And now what I can do is subtract 180 degrees. And I've got a reference angle of 10 degrees. Okay, so does that work? Well, let's see if we can draw the picture properly. So remember what 170 means. Yeah, that looks good. And whoops, I forgot to type in the actual number. 10 degrees, okay? So in other words, in the first quadrant, that's the equivalent of 10 degrees. So the final answer is 10, right? So anyway, look at it, negative 170, positive 190, the reference angle is 10. All right, so that means all the trig functions will have the same values except for the signs. And then same thing with this 135. Given the rule of thumb that I just gave you, should be clear that the equivalent positive angle is positive 225 degrees. Okay. If you add those together, you'll see that they do, without the signs, adds up to 360 degrees. All right, so in other words, negative 135 and 225 are the same angle. And now we subtract 180 and we end up with 45 degrees as our reference angle. Okay, so here I'll put in parentheses, negative 170 degrees and 190 degrees are the same angle. Just so if you're reading this later on, you'll remember where this is all coming from. In other words, right now, the way it's written, it's kind of confusing. So just a quick reminder, in parentheses, negative 135 degrees and 225 degrees are the same angle. And then you take it from there. Then you subtract 180 and you find yourself back in the first quadrant, and you'll end up with your reference angle. Very nice. I don't think Symbolab can do this for you, though. These it can do. Yes, these conversions, not a problem. All right. Now here, it's the same principle. We're trying to find ourselves back in the first quadrant, but instead of subtracting 180 degrees, we're going to do pi radians. Okay. So let's see how that works. For these cases, in order to convert these or transform these into reference angles in the first quadrant, we will subtract 2 pi radians. Okay, because 2 pi radians is the same as 180 degrees. So you're doing exactly the same thing, except you're expressing it in terms of radians. Now, let's see how this works. Oh, wait a minute. No, hold on a second. Yeah, that's right. All right, so how would that work? The first one is easy. All right, so remember 2 pi is 180 degrees. Okay, so the reference angle, in fact, if you want to look at the unit circle for a second, that means these are reference angles of each other. Remember, you have to think of it as essentially a reflection on the other side. All right, remember 60 and 240 were reference angles. So you can see 0 and 180 are reference angles. And you can see again that the signs are the opposite, but these are the same numbers. Okay, so the cosine over here is 1, over here it's -1, and these are both 0, so there's no signs. All right, so now, how about this one? Now, this is where it gets a little awkward because we might end up with negative numbers. Now, by the way, if you have, I forgot to mention this earlier, if you end up with an angle less than 90, is itself, in other words, the reference angle for 45 degrees would be 45 degrees. I just want to mention that because you're already in the first quadrant. Okay, so, before you do anything else, just check it out, look and see if you're already in the first quadrant. And in these cases, we certainly were not, so it wasn't an issue, but it could actually happen. So now here, though, 2/3 pi is the equivalent of 120 degrees. That is not in the first quadrant. So we end up with 2/3 pi -2. So let's call that 4/6 pi because we want to have a common denominator. And that means that, actually, no, that wasn't necessary. Let's leave it at 2/3. It's this one, yeah. Let's turn this into 6/3. And so we're going to wind up with -4/3 pi. Now, -4/3 is not in the first quadrant. Let's see, where is it? We have to convert it again. Okay, so the way it works with radians is okay, so -4/3 means we're going this direction. And let's see, how far is that in there? Ooh, man, this is awkward. I much prefer angles. I don't know about you. So this would be basically, all right, so let's see, this angle is, let's see, this is pi. This is 1/3 pi. So what we need is the reference angle in the first quadrant, which means coming around this way, oh man, this is awkward. Hold on, pi/2. Okay, that's 7 pi/6. So let's see, that doesn't help, does it? No. So I think in a case like this, now 2/3 pi is 240 degrees. I think that what we need to do here is try something different. Let's do this a little differently. So let's go back to the beginning. 2/3 pi would be about here. So if you subtract pi/2 from that, you're basically flipping it around 90 degrees in this direction. 2/3 minus 1/2 would be 4/6 pi minus 3/6 pi. All right, so we can go to our unit circle now and see if this is true. So in other words, we're saying that these two are reference angles, pi over 6 and 2/3 pi. No, see, that's not working either because they have to have, no, that can't be right either. All right, well, you know what? I think our best bet here, I find it very, very awkward to think in terms of radians. Why don't we do this? Just to make things as simple as possible, why don't we convert these into angles? All right, I think this will just be so much easier. Let's do this. We'll convert them into angles, and then we'll find the reference angle the normal way, and then we'll convert them back to radians, because I'm finding this to be extremely clumsy to deal with. So we'll do this. This is 180 degrees. So the first one is fine. That's not a problem. This one, 2/3 pi, is 240 degrees. And so in order to move back into the first quadrant, now 60 degrees, as you know, from up here, can be easily converted into radians by multiplying it by pi over 180. Okay, so let's do that. And so that gives us pi over 3. Now we can check and see if that's right. Okay, so pi over 3, if you look at the unit circle, let's look at pi over 3. So we can get rid of these now. Oh, no, not that. No. All right, let's try that. So let's see if we have successfully done this. So we're trying to compare pi over 3 with 2 pi over 3. Okay. Oh, I think we got a winner here, because you can see that these are the same. The cosine is 1/2. The cosine over here is negative 1/2. Now, this is the second quadrant, so only the x's are negative. So we'd expect these to be the same, but the first one's negative. So it looks like we've successfully done this. So I don't know. I think this kind of works. Just convert it to angles and then do the subtraction and then convert it back, and that should take care of it. I think this is a lot simpler than any other approach, because I just think that radians are extremely awkward to deal with. So what about this one? 5 pi over 6 is 150 degrees. Oh, okay. So because now 150 degrees is only in the second quadrant. Okay, so this is 90, and 60 brings me to 150. Okay, so we don't want to subtract 180 degrees, although I suppose we could, but it doesn't help us. So up here, Yeah, each time we subtract 180 degrees, but that's because we're already either in the third or the fourth quadrant. If you're in the second quadrant, then what you'll have to do is subtract 90 degrees. And of course, well, let's double check that one. So let's look at the unit circle for, I don't know if it has pi over 3, does it? Yes, it does. We're trying to compare it now to 5 pi over, oh. See, I don't think it has 5 pi over 6. Oh, yes, it does. It's right here. No, but you see, this one doesn't seem to have worked out. Oh, there it is. It's pi over 6. What happened here? Maybe I didn't convert this right. 5 pi over 6. Oh, there's, no, that's 150. Well, let's see. Why is this not working? Okay. Well, you can see the correct answer is 30. Yes, pi over 6. But doesn't this isn't helping, is it? 150 is not converting it back into. It is true that the answer is right here. So you know what? Let's try this. Let's do the 180. Now that's going to bring us, but that's negative 30. But wow, this is annoying. Anytime radians get involved, you know you're in trouble. All right, so if we had 90 degrees, negative 30, that means we are this coming down here. This would be the equivalent of 330 minus 180. Well, that's just bring us back to 150. That doesn't help either. All right, let's try this. There has to be a pattern here. Supposedly the rule is to subtract 2 pi. All right, you know what? Let's do this. Let's do the. Let's go back to these two. All right, let's try this again. If I go to 120, I'm doing B again just to see something. So negative 120 means you've come around this way. And that is the equivalent of coming this far, 240. All right, so that would mean that this is the equivalent of 240. And then we subtract. Now remember before we subtracted 180 and it seemed to work. And we double checked this one and it worked just fine. But then why isn't it not working here for 5 pi over 6? All right, let's see. If we do, this is 150, let's say we do subtract 360. We get minus 210. And minus 210 is equivalent to, oh, see, that just brings us right back to 150. But if we subtract 90, so we need 120 degrees. I don't know what the problem is. I really don't. I thought the rule was 2 pi. Yeah, but I mean, there's supposed to be a constant that you're able to subtract every time. And you know what? Maybe you're right. Maybe there isn't one. And it just happens to depend on what angle you have. Because there just doesn't seem to be a rule working here. It's just, in the book, it claims that if you subtract 2 pi radians from each of these, you should get the right answer. And I'm not seeing it. It's just not happening. If you take 5 pi over 6, let's say, yeah, that might be what it is, but I don't remember it saying that. It's just, there must be. You're absolutely right. It's starting to look that way. I don't know why. They didn't explain it very well then, I must say. Because you're right, we're just not getting the right answer this way. Minus 2 pi would be minus 7/6 pi, which is the equivalent of minus 210 degrees, which is 150. Right. Well, we already knew that. So what is that getting us? The thing is about the reference angle, it's with respect to 90 degrees, not 180. Because you can clearly see from the unit circle that it's supposed to be 30 degrees. Yeah, it just seems like a very strange rule that it's not the same for every quadrant. So for second and third, it's minus 180. What is okay? That may very well be. I'll tell you what. Let's just not do this on the test. I mean, this is absolutely ludicrous. I'll double check the book and see what it says again. But that was the impression that it gave me, that you always subtract, always the same, and it's just not happening. So let's just agree that we'll not do any of this on the test. Because it's just not working. All right. It's just not, we got other things to do here. Besides fool around with these, all right. So I'll go double check and see what the problem is. But yeah, without this unit circle, we'd have no way of knowing that this rule is just not working. So, all right, anyway, let's skip over this and then let's just do some of these. Now, these, again, you can do these directly in Symbolab, if you choose to do so. You can't really do it directly here, except in the sense that you could actually just say, well, listen, sine pi over 6, if you feel like going through all that trouble. All right, it's, no, sorry, it's sine pi over 6 over cosine pi over 6. And then you could look them up separately. Like if you go to the unit circle, you'll have 1/2 over radical 3 over 2. All right, so if you go to the unit circle, remember the first one is the cosine, and the second one is the sine. So you've got radical 3 over 2 over 1/2, which is the same as radical 3 over 2 times 2 over 1. So the answer is radical 3, but it might be quicker just to go to Symbolab. And that's, so tangent, let's see if it's been giving me trouble here. Pi over 6. And it's, oh, wait a minute now. What's going on here? Pi, it's saying that's pi. Did we do this wrong? It's definitely sine over cosine. And we look at the unit circle. Did I copy the wrong one? Oh, that's what, I copied the wrong one. No wonder. Okay, sorry. I realized now I copied the wrong one. It should have been. Yep, that's what I did. Let's try that again. Sine pi, I got the wrong one. It's radical. No, I didn't. Oh, yes, I did. Sorry. You know what I did? I got the order backwards. That's what the problem was. Now we're talking. Because here, this is a radical. And then we can just multiply this by radical 3 over radical 3. We're doing a procedure called rationalizing the denominator. Because it's just standard math practice to not have a square root of any kind in the denominator. I don't know why. It's just the way it's done. But anyway, now for these other ones, you could in principle do the same thing. For example, the secant, as you recall, is the inverse of the cosine. So it's 1 over the cosine of pi over 6. Okay, so therefore it's just, what is that going to be? 1 over radical 3 over 2 . And this one, you can rewrite it. And you'll end up with 2 radical 3 over 3. And of course, let's just confirm that with Symbolab. Secant pi over 6. Yeah, there it is, 2 radical 3 over 3. All right. Now, cosecant is the inverse of the sine. Okay, so it's 1 over 1/2. Oh, that couldn't be any easier. I like that. Okay, and so cosecant pi over 6. Let's see what Symbolab has to say about that. Two. Very nice. All right, and then cotangent. Well, cotangent is 1 over the tangent. Since we already have that, that will be easy. So up here, we determined that the cotangent was radical 3 over 3. And then, of course, we can take that and rationalize it. And it's just plain radical 3. Okay, very good. All right, let's just confirm that. The cotangent there you go, radical 3. All right, so those are really straightforward, but you have to remember the definitions. Either that or just throw it in the symbol lab. Okay, so those are nice and straightforward. All right, well, this is done. Let's put this aside. And what I'd like to do is now switch over to the chapter 11 material, which is more down to earth, I think, because it involves sequences and combinatorics, meaning permutations, combinations, and of course, arrangements. All right, so let's see, where is that? All right, here we go. Now, for these, you might recall that a sequence is a list of terms with a specific pattern between them. Okay, so that's the key. There's a pattern of some kind. And the pattern determines whether it is a geometric or an arithmetic sequence. How can you tell them apart? The arithmetic sequence is the one where there's a common difference between all the terms. And the geometric sequence is the one where there's a common ratio between the terms. So in the first part, we're already being told that these are arithmetic sequences. So what do we have to do? All right, so for the first one, part A, we're told the starting term is 1, and there's a common difference of 6. So therefore, the next term is 7, 13, 19, 25, and finally 31. Was that, wait a minute, is that 5? 1, 2, 3. Oh yeah, it's already done, 5. So it just keeps going. Okay. Yes, later on we can talk. All right. Now they want the 12th term. Now you can do 2 things here. You can just keep writing them out. And if you do, you'll of course get the right answer. Or the other option is to maybe use the formula that we derived. Remember this one, AN equals A1 plus N minus 1 D. And so A12, as it would be called, would be equal to, now A1 here is 1 plus, since we're looking for the 12th term, N is 12, the common difference is 6. 1 plus 66 equals 67. And if you want to, you can write them all out and see that that's correct, but that's fine. That is the correct answer. Now C, this is the tricky one. The sum of the first n terms. Now again, you can certainly add them up, but that's a lot of adding. 12 terms, yeah, that gets to be pretty big. So for this one, there's a separate formula that's specifically designed to add up the first n terms in an arithmetic sequence. All right, so n in this case, as you know, is 12 because we're looking for the sum of the first 12 terms. A1 is just simply 1. AN is the 67 that we just got through calculating. So we have 12 times 68 over 2, which equals 408. And again, you can feel free to confirm this. But yes, that's the sum of the first 12 terms. So now we're going to have to do the same thing for the first 4 parts. And this is, of course, all good practice, but it's the exact same setup every time. So let's see, let me split the screen. So, you know what I shouldn't have done? I just realized these are labeled A through D. Let me get rid of these labels here so we don't get confused. All right, so in other words, that was A. B would be this next group. Okay, so we have, this is our part B. Now, what are they telling us? They're telling us just the starting term and the difference. So in the beginning, they want to know the first 5. So it would be 10, 15, 20, 25, and 30. Very straightforward. Nice and simple. We like simple. Well, we don't necessarily need simple, but we do want straightforward. That's really the tricky part, straightforward. Anyway, so now A10, now remember here we're looking for A12. In all these cases, it's always the 12th term. So we have A12 equals, so A1, okay, this is what we're dealing with right now. A1 is 10 plus 12 minus 1, the common difference is 5. 10 plus 11 times 5 equals 10 plus 55 equals 65. Very good. And then the third part of this is to calculate the sum of the first 12 terms. All right, so we'll just use the same formula. All right, Sn equals, let me give myself some space here. Sn or actually I should say S12 in this case, is 12 times 1 plus 65 over 2. So in other words, I'm always, oh, wait a minute, sorry, the first term was 10, not 1, 10. That's better. I'm always going to need this term. The 65 has to be here. So that's one of the reasons for asking us to calculate it. So in other words, we have to have both the first and the 12th term in order to do this. So we're going to have 12 times 75 over 2, or 6 times 75, which works out to be exactly 450. And again, you can feel free to confirm this if you want, but I'm not sure if it's worth all that labor, but you can certainly do so if you want to. All right. How about the third part, part C? What's different about part C? Let me just go copy it. Now, ooh, we have negatives here. That's scary stuff. Oh, yeah, let me leave this here for a second so you can catch up. All right, so we'll be doing the exact same thing with part C, except now we've got to watch out because there are negatives involved. Negatives always increase the likelihood, in my opinion, of making mistakes, very dramatically, as a matter of fact. So what are we doing here? We've got a sequence that starts with -9, and it keeps becoming more negative. Okay, so those are my first 5 terms. And I'd like to find the 12th term based on this formula. So we have A12 equals, we started with -9 plus 12 minus 1. It's always 12 because in all 4 cases, we've been asked to find the 12th term. If we're looking for a different term, of course, that will change. -9 minus 33 minus 42. All right, and now finally we get to use our formula, our brand new favorite formula, Sn, which in this case means the 12th term. So S12 equals 12. The first term, if you recall, is -9. So now here we add minus 42. Okay, so this is going to reduce to 6 times minus 51 minus 306. All right. So it's exactly the same every time, but don't be tricked by the negative numbers or fractions if there are any. It's always exactly the same. When we get to the geometric sequences, then you have to start worrying. I mean, then the fractions and the negatives can start to become a bit of a headache, but here, not so much. All right, and then let's go to D. So once again, we start with -15, and we're subtracting 2 each time. So the numbers will become more and more negative. All right, very good. Now, again, let's use the formula for the 12th term. Okay, so A12 is -15 plus 12 times 1 times -2. And that's -37. And of course, that leaves us now with the ability to calculate the 12th term. We start with that's the 12. And then, yes, A1 is -15. As we just proved, A 12 is negative 37. And so this is the same thing as 12 times minus 52 over 2. Whoops. Equals, now these, of course, 12 over 2 can be reduced to 6. And this should give you minus 312. All right, now that's it for the arithmetic sequences. Now we're going to do something similar with geometric sequences. So these are a little more challenging. Yeah, a little bit more. Ooh, I'm looking ahead. They're getting a little tricky here. So I'll tell you what we can do, since it's already 9:30 basically. Why don't we save those for after the break, because they're a little bit more challenging. Well, yeah, you can see why, because we've got oh, actually, I forgot. There's more. Oh man, there's a lot more. All right, well, don't worry, we can do it. But I think we could use a break right about now. After all that trig, my God. So yeah, all right, so let's do this. There's a second set of arithmetic sequences. Then we get to the geometric ones, which are just a little bit more tricky. And then we'll be ready to dive back into chapter 11. Oh my God, there's 4 questions altogether. So we've done 1 out of 4, but that's all right. We'll get through these. We'll be fine. It's just that the geometric ones, and here you can see there's some arithmetic ones that have fractions, and it can get a little awkward, but don't worry, we'll see how it works. All right, so why don't we stop for a bit right about here? I think we can use a break, and then we'll finish this, and then we'll dive back into 11 and finish as much of it as we can, if not all of it. And then next week, basically, we would need to do 2 things. We would need to do the second chapter 11 problem set, which covers what we're about to do, and then the sample final itself, which covers chapter 4, chapter 5, and chapter 11. And when that's done, you'll be completely ready to do the final exam. It'll be exactly the same as those 3 problem sets, and the sample final. So, and then we'll be done with the course, and of course the semester ends next Wednesday, and so that will be it. And so, all right. So anyway, in the meantime, let's knock it off for a bit, and when we get back, we'll wrap up this chapter 11 problem set, and then go back and revisit the rest of chapter 11. All right. So see you in a while. All right, here we go. Number 2. So these are a little bit different because we already have the first 5 terms. So all that remains is to figure out the 12th term and the sum of the first 12. So we'll just keep reapplying our formulas. The difference this time, though, is that we have to identify the variables. So, for example, in this one, A1 is this first term. And you can see the common difference between the terms is 8. And so we're being asked to figure out A12 first. Then we'll do the sum. All right, so as usual, we'll use the formula. AN equals A1 plus N minus 1D. A12 equals 5 plus 12 minus 1 times 8, okay, which equals 5 plus 11 times 8, which equals 5 plus 88, which is 93. And then that's the first part of this. And then we need the sum. Okay, let's get that going. We have Sn equals N times A1 plus AN over 2. So that we'll have, so if we recall, A1 was equal to 5 from way back there. And then the number we just calculated, 93. So 12 times 98 over 2. And you can simplify this to 6 times 98. And so 6 times 98 is 588. Beautiful. So that was easy. So now the second one. Whoops. All right. So let me leave it there for a second so you can catch up. All right. Now the next sequence, you can see here, A1 is clearly 2. And the common difference is just 10. All right. That's nice and straightforward. So once again, we'll apply these two formulas. So A12 in this case would be 2 plus 12 minus 1 times 10. (112). That is the 12th term. And then we can use that information to calculate the sum of the first 12. Okay, so that's 12 times 114 over 2, which is the same as, oops, 6 times 114, 684. So yeah, I mean, the logic is the same in each case, but we just have to be a little careful with some of them. All right, so now how about this one? Now with this next sequence, the first term is 50. The common difference this time, though, is negative because they're shrinking. Each time they go down by 2. So D is -2. And so AN equals A1 plus N minus 1D. A12 is 50 plus 12 minus 1 times -2. All right, so whatever this number is, it'll be smaller than 50, of course. So we end up with 50 minus 22, which means, of course, 38. 28. All right, so if we keep going, the 12th term will be 28. So now, of course, our objective is to find the sum of those first 12 terms. And since they're shrinking, the sum won't be as large as you might think. It won't be huge, let's put it that way. All right, so the first term was 50, the last term was 28. All right, so now you've got 6 times 78, and that's equal to 468. Nice. Okay, so that wasn't as bad as it looked. But yeah, you can see the sum is a little smaller than you might think because the numbers are shrinking. Now the next one, we have to watch it because there's fractions involved. And fractions are always going to make things a little more challenging. All right, let's skip. What do I mean by that? Well, look, if you look at those fractions, you'll see the pattern is hard to determine. So here our strategy is going to be a little bit different. What we're going to do is find a common denominator and rewrite the sequence a little bit so that it becomes more clear what pattern we have. In fact, if you look at it the way it is, you might not even realize that there is a pattern until you start to change things. So in other words, why don't we have a common denominator of 24? By doing that, we'll have 3 24ths, 19 24ths, 35 24ths, and then we multiply 17/8 by 3/3 to come up with 51 over 24, and then 67 over 24. Okay, so now by writing it like this, we can have A1 equals 3 24ths, while D is 16 out of 24. Now, you could reduce these a little bit, but we may as well keep them like this for now because it might be easier later on to use our formulas if they all have the same common denominator. Like, for example, 3 over 24 is clearly 1/8. D is 16 over 24. That's equal to 2/3, but why don't we just leave it like that for now? When we use our formula, so let's plug everything in here. All right. And that equals 3 over 24 plus 11 times 16 over 24. So this actually, let's do this over here. 11 times 16 over 24 is equivalent of 11 over 1 times 16 over 24. So you've got 176 over 24. So that term is 179 over 24. Again, you actually might be able to reduce this a little bit, but let's just leave it like this for the sum formula. By keeping everything in 24ths, most likely that'll speed things up a little bit. And then so Sn, of course, we're very familiar with this now. As 12 is equal to 12 times. So the first term, if you recall, was 3/24 or 1/8. The last term is 179 over 24. Yeah, so you can see it's getting a little challenging here. In the numerator, we have 182 over 24. In the denominator, we have 2. So dividing by 2 is the same thing as multiplying by a half. So let's see, what can we do here? All right, so we can simplify this. 12 divided by 48. Let's write this as 182 over 4. 91 over 2. That's as simple as it's going to get. All right, because clearly 91 is an odd number, and I think it's even prime. So we'll just leave it like that. Wow, what a mess that was. 91 halves is our sum, and the 12th term was 179 over 24. Ooh, I'll give you a second to recover from that one before we do the next one. All right, now this one is also involving fractions. It's not quite as messy as the previous one. There's only one real change that we should probably make, and you can probably guess what it is right off the bat. Let's convert them all into tenths. Why not? So now it should be clear. Well, first of all, the first term is 5/10, and the common difference between them is 4/10. And again, we'll leave these as fractions, even though, or as tenths rather, even though it's pretty clear that we could reduce these if we needed to. So the 12th term will be attained the usual way. So we'll have A12 is 5/10 plus 12 minus 1 times, the difference is 4/10. And so we'll have 5/10 plus 11 times 4/10. All right. And so it's 49/10, and we can just leave it like that. There's no point in trying to reduce it. There's nothing we can really do with it. And then now we can, of course, go ahead and calculate our sum. All right, let's see what that is. Whoops, let's get this up here a little better. There you go. All right. So the first term we converted into 5/10. The last term is 49 over 10. So we have 54/10. Now 12 divided by 2, of course, is 6. So let's just rewrite it as 6. And then we have 3/24 over 10. That's good enough. You can simplify it, but we can leave it like that as well. All right, so now in part 3, we're switching over to geometric sequences. All right, so everything we just did will apply now to geometric sequences. All right, so the formulas are different, of course, and the results will be, in some cases, very, very large, or possibly very, very small, because the terms increase or decrease very, very quickly compared to arithmetic sequences. All right, so let's see what we're dealing with here. So here we'll go back to finding the first 5 terms, the 12th term, and the sum of the first 12 terms. Okay, so we have 2 examples. So let's remind ourselves what formulas we're supposed to use. We can start the first 5 terms. We start with 12, and we're doubling each time. Each term is double the one before it because we have a common ratio of 2. All right, and that's it. Those are the first 5 terms. So what about the 12th term? Now here, the formula is a little different. If you remember, the formula here is an is a1 times r to the n minus 1 power. So in a way, it's almost simpler than what we were doing before. We have 12 times 2 raised to the 12 minus 1 power equals 12 times 2 to the 11th, which, as you can see, it's going to be a pretty big number. It's actually 12 times 2048. And finally, it's equal to 24,576. All right, very good. So that wasn't too bad. Now the sum is a little bit messier. All right, the sum formula is kind of a headache, as a matter of fact. We have a1, 1 minus rn. Now it doesn't look that bad, but it can get very messy in a hurry. So here, for example, you've got S12 would equal, the first term was the 12, 1 minus 2 to the 12th. All right, so let's see what this gives us. Now 2 to the 12th is 4096. That's all divided by -1. The negatives obviously cancel each other out. So when you multiply that out, you should get 49,140. All right, so 4095 times 12 is 49,140. Perfect. All right. Now we'll do the same thing here. So first we need the first 5 terms. Okay, well, that was easy. Now the 12th term, would be 8 times. Oh, yeah, the common ratio is 3. It says it right here. 3 to the 12 minus 1 power 8 times 3 to the 11th. And that's 177, 147. So it's 1,417,176. All right, very good. So now we're ready to calculate the sum of the first 12. So the formula again is Sn equals A1 okay, 1 minus r to the n over 1 minus r. All right, the first term was 8. The common ratio was 3. Yeah, this is going to be a big number. I mean, a really big number. 3 to the 12th power is equal to, wow, 531,441 over -2. So if you take 1 and subtract 531, 441, it'll give you negative 531, 440. Now, obviously the negatives will cancel, so this reduces to negative. Ooh, not negative, positive 2,000,000 125,760. All right. So that's actually it for question 3. So the fourth and final question is another question about geometric sequences. These are a little bit more challenging because they involve fractions and potentially negatives. Ooh, yes, they do. But we know how to handle them. That's okay. All right, let's go ahead and see what they're all about. So this time we've got the first 5 terms. We don't need to do the first 5 already or again, but we do have to identify the appropriate terms that we need for our formulas. For example, here A1 is 4 and the common ratio is 3. So we need the 12th term. Four times 3 to the 12 minus 1. And that equals 708, 588. So you can see it gets big really fast. All right, then when we apply our formula, all right, 4 times 1 minus 3. Oh, I almost forgot. Yeah, make sure that this exponent stays inside the parentheses. So 3 to the 12th. There it is again. We saw that number before, 531,000, just a coincidence. All right, so we'll have And so what does that end up being? $1,062,880. Okay. Now for the next one looks pretty straightforward. We start with 6, obviously, and we have a common ratio of 2. Okay, whoops. So yes, all right, so we have A1 is 6, R is 2. So we have 6 times 2 to the 12 minus 1 power. 6 times 2 to the 11th. 6 times 2048, which is 12,288. And of course, our formula for the sum is A1, 1 minus r to the n, all over 1 minus r. 6 times 1 minus 2 to the 12th. Okay. Equals 6 times 1 minus, so 2 to the 12th is 4096. The negatives cancel each other out, and we are left with 24,570. Okay. So that one was nice. That one worked out really easily. The next one, well, maybe not so much. The next one involves fractions, unfortunately, and they're not very, well, they're not ugly fractions, but they're still fractions. All right, so first things first, A1 is a half, and the common ratio is 1/2, because how do you get from one term to the next? You're multiplying the previous one by 1/2, or 1/2. Okay, so that's, it's a little tricky. But anyway, so AN so I'll have 1/2 times 1/2. So 1/2 times 1/2 to the 11th, which is actually 1/2 to the 12th. Or you can rewrite it as 1 to the 12th over 2 to the 12th, 1 over 4096. All right, now let's not convert that into a decimal because it's just a mess. Let's just leave it like this. All right. And then, of course, we have to follow up with the sum. So we'll have 1/2, 1 minus 1/2 to the 12th. So really, the bottom line is you just have to be careful with these. They're not conceptually difficult. Now, 1/12, 1/2 to the 12th, like we saw up here, is 1 over 496, 4096. And 1 minus a half is a half. These just drop out, which is kind of nice. So how do I combine 1 minus 1 over 4096? I need a common denominator. I can convert that 1 into 4096 over 4096. So we're just going to wind up with 4095 over 4096. And that's it. Again, you can convert into a decimal. There's no point. It's like 0.99999 something. 4095 over 4096 is perfectly fine. Let me just clean that up a little. Ooh, let's see what's going on with this one. So A1 is 2/3. The common ratio this time is 1/3. Okay, if you multiply each term by 1/3, you'll move on to the next one. So therefore, to come up with the 12th term, you'll have 2/3 times 1/3 to the 11th power. Let's see if we can simplify this a little. Let's rewrite this as 1/11, 1 to the 11th over 3 to the 11th. And then now, of course, 1 to the 11th is just 1. And that means down here, we actually have 3 to the 12th. And 3 to the 12th is, of course, an enormous number. Yeah, there it is again. We keep seeing this number over and over again. 531, 441. All right, well, it is what it is. All right. It's not a secret code or anything. It's just a coincidence that we keep bumping into that 531,441. All right. Now you can see the calculation of S is going to be a bit of a mess. Oops. Yeah, look at this. Oh my God. 2 over 531,441 times 1 minus 1/3 to the 12th. Ooh. All right, well, let's do it. Add the denominators. Where's that? Well, we need to convert them. What part are you referring to? Two-thirds. Yeah. No. Oh, no, because you're multiplying. You're not adding, you're multiplying. And you're multiplying. The second one has a different exponent than the first one. So you would never just add them up. I mean, you're not even multiplying. You're multiplying 2/3 by not 1/3, but by 1/3 to the 11th power. So you have to deal with that exponent first before you do anything else. Okay, so in other words, here what I actually did here. This 2/3, I'll move this over here, 2/3. I may have left out a step. It's 2/3 times 1/3 to the 11th. That's where this comes from. 2, we multiply 2 by 1. And here, when you multiply the 3, there's an implicit exponent of 1 here. So if you notice, 3 to the 1st times 3 to the 11th is 3 to the 12th. And then we calculate this value of 3 to the 12th. So there's no adding because first of all, you're multiplying, and secondly, because you have an exponent rate, the 1/3 is raised to an exponent, 2/3 is not. Okay. All right. So yeah, ooh, what a mess. But all right. So this is that 531 number that we keep seeing. And don't worry, we'll get there. It's going to be a mess, but we will survive. Now, in the denominator, 1 minus 1/3 is just 2/3. All right, so what we should probably do is consolidate these two. So I'd like to rewrite this 1 . Okay, so now it's easier to consolidate these. Well, a little bit easier. Okay, there's got to be a way we can simplify this. I think there is. What I'm going to do is leave the numerator the way it is. And what I'm going to do is rewrite the denominator in terms of this 531, 441. So how do I do that? Oops. Here we go, 531, 441 over itself gives me, $1 million. Wow, I'm not even sure if this is helping or not. I'll tell you what, let's leave it like this. Basically what I'm trying to do is get some cancellation going on. So let's leave it like this. All right. Oh God, what a mess. So basically, I'm going to multiply the numerator by the inverse of this denominator right now. You know what? This didn't do any good. I just realized I'm just, yeah, it's just, oh, you know what? I just realized, I'll tell you what, there's the reason why this is such a mess. I made it an incorrect substitution way up here. No wonder it's not working out. All right, hold on. I copied the wrong thing. That's why it's turning into, I mean, it's not going to be an easy answer, but it's not going to be this disastrously bad. I just noticed it now. I accidentally substituted an A12 instead of A1. All right, so that should make things a little cleaner. Yeah, look at this mess. We can get rid of all of this stuff. There you go. That's the problem. Yeah, I knew it couldn't be this bad. All right, I'll tell you what happened. I made a bad substitution up here. That A1 is 2/3. I accidentally put in A12 instead of A1. That's where we went wrong, or that's where I went wrong. The ratio is 1/3. Wait a minute, that can't be right. Yes, yes, yes. So the ratio is 1/3 to the 12th power. All right, now we're getting somewhere. See what I did? I accidentally put A12 over here instead of 2/3. Now that's a lot simpler. All right, so 2/3 times 1 minus 1/3 to the 12th. Now here's one of the nice things about this problem. Those 2/3 will cancel each other out. That makes things even nicer for us. So then we're left with something relatively simple. 1 minus 1/3 to the 12th. Now remember how I did this before. This is the same as 1 to the 12th over 3 to the 12th. So there's that old familiar 531,441. So now I'd like to consolidate these into a single ratio. And then that means that in the numerator, I have 530,440. And down here, I've got, I've got 531,440. Yes, okay, so it's going to be just a tiny bit short of 1. There we go. So after all that, this is our final result. So this is what happens when you have messy sequences. It's easy to make mistakes, very easy. All right, so after all that's what we were aiming for. All right, so there's one more. Now this one is different because it has fractions not fractions, negatives rather than fractions. They're not, it's not that much more difficult, but it does make things a little bit trickier. All right, so finally we have A12, or first AN, A1, R to the N minus 1, minus 3, Oh yeah, let's don't forget, A1 is 3. The common ratio is actually -5. It's negative because the signs alternate back and forth between positives and negatives. So that's an important detail. The ratio is negative. If you didn't get that part, of course, you'll end up with the wrong answer here. All right. So you've got -3 multiplied by negative, wow, this is a big number. -48, 828, 125. And when you multiply that by -3, it's gigantic. Yes, it's absolutely huge. It's 100. Oh, let me fix that. It's going to turn out to be positive. There's two negatives here, so it's positive 146 million 44,375. That's our 12th term. So you can imagine what the sum is going to look like. Whoa. Well, not necessarily. Now remember, half the terms are negative and half of them are positive. So the sum might not be an enormous number. All right, so we'll have the first term was -3, way back in the beginning. The common ratio is -5. Oh, whoops, not 1 minus. It's just plain -5 to the 12th. I wrote, of course, the wrong thing here. Hold on one second. No, I had it. Sorry. Wait a minute. Sorry. Yep. Let's try that again. God, there's negatives everywhere. Look at that. All right. So, yes. So finally, when the dust settles, we have -3. A1 is -3 times 1 minus -5 to the 12th over 1 minus -5. So it's an absolute disaster. But if we're careful, we should be fine. -3, 1. Well, this can't be consolidated. 1 minus -5 to the 12th is then divided by, now here we've got 1 minus a -5, which is 6. All right, that helps a little. Now, -5 to the 12th is going to be a positive number, a very large number. Wow, 244 million 140,625, all divided by 6. Wow, that's getting up there. So we'll have -3 times minus 244 All right, so that's minus 244,140,624 over 6. All right, we'll multiply that out. Now, clearly, the negatives cancel each other out. This will be a positive number. So it works out to be 122 million 70,000 that is, and 312. Now, interestingly enough, if you look at the 12th term, that was 146 million some odd, thousand. The sum is actually smaller than the first term, and that's because the terms alternate between positive and negative. So it didn't turn out to be that astronomical after all. And that's again because of the rotating signs. All right, well, this one is done. So that was a lot, but now we are experts in this area, as you'll see. And now we're ready for something completely different, which is more conceptual than computational. These require a lot of grinding through formulas, whereas what we're about to do not so much. It's more conceptual, which you might find more interesting. I don't know. We'll see. But we're about to finish up chapter 11. And when that's done, or at least we'll try, we'll get as much of it done as we can. Then, of course, the last steps next week are the second chapter 11 problem set and the sample final. And that's it. We're done. All right. We're done with pre-calc. So either you're going on to Calc 1 or else this is your swan song in math. It could be either one. I don't know. But anyway, so let's go on to chapter 11. All right, we don't need this chapter anymore. Let's get rid of it. And I don't think we need Symbolab. So let's go right back to 11. Now, we're going to introduce the so-called rules of probability. Now, remember, this second half of this chapter is all about probability. The first half was more about sequences and combinatorics. This is now our first proper look at actual probability theory. So remember, what's happening here is that we're assuming that there's a process of some kind that is generating outcomes where we know in advance what the possible outcomes are, but we certainly do not know what they'll actually be. And so, there's a lot of possibilities, and we went through some examples with the dice. We were looking at the cases where we only cared about evens and odds. And so we don't need to go through this again, but let's just go ahead and take a quick look at these rules. Now, there's 3 of them. Well, there's actually more, but there's 3 that we want to consider. So they are the so-called addition rule, complement rule, and multiplication rule. And these enable us to calculate probabilities for fairly complicated situations. All right, more so than just rolling a dice and seeing how many times it turns up even. Okay, when we have more complicated situation, we need a set of rules to help us determine what to do. All right, so we'll start with the addition rule. And you'll see it's pretty straightforward. You've got, now, by the way, let's remind ourselves what these symbols mean. This is the symbol for union. And what this means is that I'm consolidating 2 sets. So just as a quick reminder, let's say that A is the set 1, 2, and 3, and B is the set 3, 4, and 5. Well, the union of A and B is the set containing 1, 2, 3, 4, and 5. So this is the probability of that happening. In other words, one or the other events being true. So imagine this is some kind of game where a number from 1 to 5 is randomly chosen, or something along those lines. We want to know the probability of getting a number between 1 and 5. Now, this symbol is intersection. This is a set that contains elements that are common to both. So in this example up here, that means that A intersect B would just be 3, because that's the only element they have in common. And then here, of course, you've got the probabilities of A and B individually. So that's what we have to do to come up with the probability of a union. All right. Now, let's take a look at an example. So first, going back to the original experiment that we had in this section, we have a sample space consisting of the values EE, EO, OE, and OO, which refer to evens and odds. So for example, OE means getting an odd followed by an even, EO means even followed by odd, et cetera, et cetera. So imagine the following two events that we can define. The first roll is even means either we have EO or OE. I'm sorry, not EO. EO, yes, but EE is another possibility here. Each of these, by the way, these are events. And remember, we define these are as subsets of the sample space. So they're sets themselves, and they're completely contained within the sample space. And they can actually have anything. We can define them any way we like, as long as we end up with elements that belong to the sample space. Now here in the second case, we have exactly one roll is odd, which means EO or OE. Because you can see exactly one roll is odd in both of those cases. Now, what are we trying to do? We're trying to calculate the probability that one or both of these is true. All right, so in other words, we're calculating the probability of a union, and for that, we will use the addition rule. All right, here we go. So the question is, what is the probability that either A or B is true? Or in English, what's the probability that either the first roll is even or exactly one roll is odd? Suppose that we're playing a game of some kind, a gambling game where prizes depend on this happening. What's the probability of winning a prize? It's a good question. All right, so we already know what elements belong. Oh, one more thing we need to do. We need to identify the intersection between the two. That simply represents the points that are in common to sets A and B. That's just one element, which is EO. Now, you might remember we had this discussion last time. When we have something like this, remember the way we defined this experiment was that we roll the die twice, and each time we observe whether it's even or odd. Since getting an even and an odd are equally likely, that implies that each element in our sample space is also equally likely. Okay, and since there's 4 elements, that simply means that each one has a probability of 1/4. And so that makes things a lot simpler for us. Because to calculate the probability of A or B or A intersect B, each one of these outcomes is also equally likely. So therefore, the probability of A, for example, equals the probability of EE plus EO, which is 1/4, plus 1/4, which is 1/2. And same thing with B. This is the probability of getting either EO or OE, which is 1/2. And so therefore, The probability of this intersection is just a quarter. So now we have all the information we need to apply our addition rule. All right, so I know it's getting a little crowded in here, but I just wanted to make it clear that, well, you'll see why in the next slide. I've consolidated all of these probabilities. I wanted you to remember why these probabilities are what they are. All right, so let's just quickly look at the next slide. So again, the probability of A and B are both a half, and the probability of A intersect B is a quarter, for the reasons that I mentioned in the last slide. It has to do with the way the sample space was constructed. But once we have this information, now it's a very simple matter to plug them into the addition rule and come up with our probability. And here we go. So there's the addition rule. We'll just plug in the numbers, and yes, we do end up with 3/4. All right, now as it turns out, as is so often the case in math, there's more than one way to get to the same result. Here's another option that we had available to us. What if we had done this? What if we sat down and just simply wrote out all the elements that belong to this union? All right, so if you recall, remember A was EE and EO, and then B was EO and OE. So therefore the union would have been, and you just combine them all, and based on our understanding that each of these elements is equally likely, that implies that the probability of A union B is just 3/4, 3 out of 4. So that gives us a second alternative for calculating the same result. And it also means we can double check our results from the addition rule. Now, I just want to point out, though, that in some circumstances, you don't have the ability to do the same calculations in two different ways. You may only be restricted to one specific way, but in this case, we have different ways we can get to the same results, and it makes sense to check them all out to make sure that they all agree with each other. That's a great way to double check your results. You don't have to, but I think it's a good idea because you know how easy it is to make mistakes with this stuff. Very easy. Crazy easy, as a matter of fact. All right, so there's our classic example of the addition rule. Now, it turns out, though, that there's a simpler version of this rule that we can use under certain conditions. Now, the rule isn't that complicated to start with, let's face it. But anything you can do to speed things up is very much welcome. I think you'll agree. All right, so now what happens if A and B have no elements in common? Yes, that's what we were doing last week. Yes. Were you not here last week? You were. Oh. All right. Well, why don't you go back and reread the beginning of this chapter? It's all here. Let's go back up here. We did the combinatorics and the sequences. And then I think we may have started to do probability theory. Yes, we just started it, basically. We did review some basic concepts, and we discussed the sample spaces here. Oh, here we go. Yes, we did a brief review of sets right here on slides 115 and 116. I mean, I obviously edited during the lecture, but yes, this is our quick review of probability theory. Maybe, I don't know. I mean, I only spent a few minutes doing this, but if you want to go over again right now, that's fine. Is it, no, you did it not get in? How did it not get into the video? Okay, I'm not sure what's going on then. I mean, these are the notes that I posted on Moodle. I, is it possible that the video stopped recording? I don't know. I mean, all right. Yeah, go back. Let me know if any of this stuff is missing. As far as I can tell. Yeah, I mean, but yeah, it's all here. I mean, if you go into Moodle, I just picked up the slides that we used last week and I'm adding to them right now. Whoops. So I know we did all the combinatorics. Yeah, I mean, we must have done this. Otherwise, all this handwriting wouldn't be here. All right. Well, all right. So you double check and see what happens. Let me know. All right. Well, anyway, oh, so yeah, back to this. Let me do one thing here. Update the date on these notes. Yeah, okay. So this is like what we did last time, plus more good stuff. I left in all the old handwritten notes because I want you to have them, of course. All right. All right. Anyway, so what happens if the two events are mutually exclusive or disjoint? In other words, you might recall we discussed this. The idea of being mutually exclusive is that two events cannot both be true at the same time. Two things that cannot both be true. Like, for example, if I picked a random number, it can't be both even and odd. So that means that those are mutually exclusive events, being even and odd. And so in that case, you can tell because their intersection is the empty set. So if, let's go back to this example I had before. Let's say we had A equals 1, 2, and 3, and B is 6 and 7. Well, then here we can say that the intersection is empty. There's no elements they have in common, and A and B are said to be mutually exclusive. Meaning they have nothing in common. And that implies that the probability of this happening is 0. Again, it's like, imagine that I had, instead of those numbers, I had the odd numbers and the even numbers. Obviously, their intersection is empty. There's no number that is both. Okay. So that's what this concept means. Now, why does this matter here? Because if you look at this rule, the original rule requires us to calculate A, the probability of A, plus the probability of B, minus the probability of A intersect B. But if this probability is 0, then we don't need to include it at all. So in other words, all we have to do now is calculate the probability of A plus the probability of B. And that's it, we're done. So we have this slightly simpler version that we can use, but only when we have mutually exclusive sets or elements. All right, so here's a quick example using, again, the same setup. So our sample space is EE, EO, OE, and OO, each of which is equally likely. The first roll is even would be the set containing EE and EO. And the first roll is odd would be OE and OO. And you can see they have no elements in common, which means that it's not possible for both of these things to be true at the same time. All right, so if that's the case, what if I'm looking for the probability of A union B? All right. Well, I don't know how this is possible. Apparently the video doesn't include this stuff. So we're going to go back and start a backup here. I don't know how this is even possible, but so let's go back to Haagen-Dazs and we'll pick it up from here. I thought we did this stuff. I really did. So I don't know what's going on, but let's try this. All right. So we just go back to the beginning. And we'll start at the beginning. I mean, I thought this was done, and I don't know how it's possible that the handwriting got there, but okay, well, let's carry on. Let's go back to the beginning and assume that we haven't seen this before. So, so we'll start out by introducing probability theory. And this is a mathematical framework for measuring uncertainty. And it's based on the concept of the random experiment, which means that we have something going on which generates outcomes in such a way that all possible outcomes are known in advance, but yet the actual outcome is not known in advance. So We see, for example, cases like spinning a roulette wheel, choosing a card from a deck, and rolling a pair of dice. These are all considered the examples of random experiments because you can see that, when you roll the dice, when you pick the card from the deck, when you spin the wheel, we know in advance what might happen, but we do not know what actually does happen. So let's say that, for example, a die is rolled twice. So this is an experiment that we'll want to look at over and over again throughout the rest of this chapter. So suppose that we don't really want to know, or we don't need to know if the number of the die is 1, 2, 3, 4, 5, or 6, but instead, for whatever reason, we're only interested in whether it's even or odd. Well, that means that if we roll the die twice, there's only 4 things that can happen. We can either get even followed by even followed by odd followed by even, and odd followed by odd. And because of the way we set up this experiment, each of these is equally likely to occur. All right. Now, if you can write out all the possibilities if you want to and see that in 1/4 of the cases, you'll get even followed by even. In 1/4 of the cases, you'll get even followed by odd. In 1/4 of the cases, you'll get odd followed by even. And then finally, you'll get, in 1/4 of the cases, odd followed by odd. Now, just a little fun side note. Dice is the plural of die, in case you didn't know that. Okay, so now each die has the same number of odds and even numbers, which implies that the probability of an odd and an even are both equal to 1/2. They're both equally likely. So that means we have 2 rolls, 4 outcomes, each of which is equally likely to occur. In other words, any one of these has a 1/4 or 25% chance of showing up. That's important, as you can see in our calculations. It doesn't always work out this way, and if it doesn't, then our results will be much more complicated. Now, by the way, just as an aside here, the number of times that I roll the die will determine how many possible outcomes there are in a very specific way. It turns out that every time I roll the die, the number of possible outcomes will double. So here's a little diagram that you can use to help yourself keep track of how many outcomes are possible when you roll the die twice. So the first roll brings us even or odd. Now, once you have an even, you can follow that up by another even or an odd. If you start with an odd, you can follow that up with an even or another odd. So there's 4 possibilities here. But if you roll the die a third time, it's starting out with 2 evens, we can follow with an even, you can follow with an odd, and you can see across the board, altogether, there are 8 possibilities. And again, because of the way this experiment is taking place, each one has a 1/8 or 0.125 probability of taking place. So in other words, each one is 1/8, has a 1/8 probability of occurring. The sample space is simply a set that contains all these outcomes. So we're going to restrict ourselves to the case where there's 2 rolls. And so therefore there'll be 4 outcomes, and these are the 4. And this will be the basis for all of our calculations that follow, because all the probabilities are defined with respect to this sample space. Now, it's very convenient here that we have all 4 possibilities being the same, because it doesn't always work that way. And so in some of our results, it'll be quicker and easier to calculate probabilities this way. But we also would like to understand the most general approaches, which allow us to do the same probabilities when each outcome is not equally likely to occur. All right, so here we go. Let's do a quick review of set theory. So we've got 4 sets, A, B, C, and D. And of course, a set is simply a collection of elements. The order in which I write them is not relevant. So we have some basic set algebra we'd like to be able to apply to these sets. The first one is union, which is designated with the not exactly the letter U, but a symbol that looks like a U. And basically what it's telling us to do is simply combine those two sets. So for this one, A and B, when you lump those together into one big set, you'll get 1, 2, 3, and 4. And now if you notice, the two sets both have 2 and 3 in common. There's no need to write those separately. All we need is the unique elements that are common to both. So the union can be simply written as 1, 2, 3, 4. In English, we sometimes hear that expressed as A or B. All right. So you can pronounce this A union B or A or B. It means the same thing. It's a new set that is simply the combination of the existing sets. All right. That's what union means. Now, intersection is very different because with intersection, what you're trying to do, and these are the same sets, by the way, you're trying to identify the elements that are in common to two sets. So here, for example, if you look at A and B, their intersection is simply the element 2 because that's the only element that they have in common. So this upside down U looking symbol is intersection. This is the equivalent of and in English. Okay, that's intersection. And here, though, it turns out that you do not always have an intersection, though. If you look at C and D, for example, they have no elements in common. And so let's go to the next slide here. And you'll see, in fact, I'll write it up on the top here. C and D have no elements in common. And you can see why. I mean, they do not have any elements in common. And so we can write this as the intersection of C and D is the empty set. And this implies that their probability of this happening, although this is not part of set theory, I just want to remind you that that means that this probability is simply 0. And we also say that C and D are mutually exclusive. All right, so that's an aside here. They have nothing in common, therefore they're said to be mutually exclusive, and their intersection is empty. Okay, so those all represent the same concept. Down here at the bottom, A and B do have an element in common, 2, so therefore the intersection there is just 2. Now, the third concept that we want to review here is the notion of subset. A subset means that one set is completely contained within another. So if you look carefully at DNA, D contains elements 1 and 2, A contains elements 1, 2, and 3. We therefore say D is a subset of A because all the elements in D are also elements of A. Now, there's also a concept that we need to consider here as well. Let me just see if I did. Yes, that's coming up. I just wanted to give you another example here, which is more kind of real world-ish. And that is the idea that, let's say we have two sets, which are students now. And let's say A is all SUNY Purchase students, B is all the art majors. Therefore, B is a subset of A because in order to be an art major at SUNY Purchase, you must also, of course, be a student at SUNY Purchase. Okay, that was just meant to be a quick real world example. Now, It's not always the case that every set is a subset of every other set, of course. So here, for example, if you look at the sets C and D, it's pretty clear that C is not contained within D. So here we say that C is not a subset of D, and we represent that with that little slash to the subset symbol. So remember, this means subset. It looks like a C. Let me try to draw it a little better. That's a little better. And then this would be not a subset. All right, so now that's what we needed to review here. And then what we need to do is introduce the concept of an event, which is itself simply a subset. All right, so the basic principles of set theory are what's determining all of the results in probability theory. So therefore, we're going to introduce this concept of an event, and an event is defined as a subset of the sample space, and it could be literally anything. So down here, for example, based on our experiment with the dice, F is at most one even number turns up, which simply means you only get one even or no evens. We're disallowing for the possibility of two evens. And so it's pretty clear that F is a subset of S because all the elements of F are subsets or contained within S, and therefore that means that F is an event. Now that's interesting, but what we really care about is calculating probabilities for events. That's our main interest here. All right, so what we're going to do now is try to calculate the probability of F. And there's, again, as usual, a couple of different ways of doing this. So now, first things first, we note that, as I said earlier, each element in S is equally likely to occur. Each element has a probability of 1/4 for that reason. And so we can write that out here on the next slide. And I mean, clearly all I've done is written out the idea that the probability of each element is 1/4. And so that's going to help us with our calculations for any event that we choose to define. And you'll see that it makes things a lot simpler when they're all equally likely. So let's go ahead and see how you would go ahead calculating the probability of F. Well, we can break it down into its component elements and calculate each element separately and then add them up. And that certainly will do the job. So here we recall F is equal to EO, OE, and OO, which implies that this must be true. The probability of F is the sum of the individual elements probabilities that compose F. And each of these we already know has a probability of 1/4. So when we're done, we can see that this probability is just 3/4. That's one approach. Now, I just want to point out here that the approach we've just seen here will always work, regardless of whether these elements are equally likely or not. So this approach always does the job. But sometimes we like to take advantage of special cases, like when the elements are all equally likely, and streamline things just a little bit. And so the next slide shows how you can do that when all the elements in a sample space are equally likely. What we could do in this particular case is just say, well, listen, F equals EO, OE, and OO. And S, of course, remember, we'll just rewrite that, EO, OE, OO, EE. So what this is saying down here is that there are 3 elements in F. and there are 4 elements in S. So because of these special circumstances, you can just go ahead and say, well, there's 3 elements in F and 4 in the entire sample space. Therefore, the probability is 3/4. And that's it. You're done. Look how easy that is. But again, this only applies to cases where the elements are equally likely. Now, I did have an example here where they're not equally likely, just so you can see how that would work. And I think when that part is done, we really are caught up. All right. And then we can get back to our rules. So if I really don't know how in the world this handwriting got in here if I didn't cover the material, but it's possible that I wrote it in advance and I just plain forgot about it. That's always a possibility. I was just surprised. But anyway, it doesn't matter now because we're all caught up, or we will be when we look at this one last example, and then we can get back to our rules. All right. So what if we had the following scenario? We're rolling the dice, but now we're using special dice. These are oddball dice. These are not normal dice. These contain 2 even numbers and 4 odd numbers. Wow, that's a weird set of dice. But what that means is that while there's still only 4 things that can happen, they're not all equally likely to occur. No, and that changes everything. In fact, I'm going to show you in the next slide what that does to our probabilities. And then we're going to do some more calculations with this special case where we do not have all equally likely elements. All right, here we go. So because there's 2 evens and 4 odds, the probability of getting an even is 1/3 instead of 1/2 or 2/6. And then the probability of an odd is 4/6 or 2/3. And that changes everything because you can see the probability of getting 2 evens is 1/3 times 1/3, which is a 1/9. Oh, that's okay. All right, go ahead. If you need to get in touch with me, send me an email. And also, yeah, we have to discuss your, the format of your midterm because I wasn't able to open those pictures. So we'll have to try that again. Yes, yeah, go ahead. Whatever it takes. Yes, go do what you have to do. And then just try to resend everything in a way that if you have to put one on each email, do it because the memory constraints are pretty tight. So just do whatever you have to do. All right. I'll see you next week. All right. Anyway, so let's get back to this. So you can see then EO would be 1/3 times 2/3, which is 2/9. OE is 2/3 times 1/3, which is 2/9. And OO would be 4/9. So instead of having all 1/4, we have 1/9, 2/9, 2/9, and 4/9. All right. Now let's go ahead and ask some more questions and see how things are different now compared to before, where they're all just the same. All right. Well, let's use the same definition for F, the probability that at most one even number turns up. And we're going to see that instead of 3/4, it'll be a very different number. All right. Are we ready? Yeah. I can, it was such a while ago. I must have sat down and said, let me add some more examples here. And then when I saw the handwriting, I assumed that I'd already covered that. That I can't imagine any other explanation for how this happened. But anyway, these are good examples. They're in the slides and they're there for your benefit. So now look what happens this time. Same setup, everything's the same, except instead of having a quarter plus a quarter plus a quarter, I've got 8/9 as my probability. So here, what I cannot do, it's not 3/4. unlike the last time. And that's because they're not all equally likely. Well, that's the key point of all this. Okay, now we're ready for the addition rule. All right. So the addition rule, now we already are experts on the addition rule. Hopefully after the fact, it makes a lot more sense. So we've got 3 rules that we'd like to introduce that make it possible for us to calculate more complicated probabilities. And so this is the one that involves unions. Okay. And so we can see, we've already seen that we add up these 2 individual probabilities and then we subtract their intersection. And in fact, we were doing one right here. So the sample space, now remember, we're back to the case where they're all equally likely. Okay, forget this last example. Now we're back to assuming that they're all equally likely. And so these are our subsets or events. A contains EO and OE, B contains EO and OE. And we'd like to know the probability that either of them, one or the other, occurs, which means we're looking at a union. And so imagine we're winning, let's say we're playing in a casino and we'll get a prize if we either get A or B. And so therefore, it's very important to know. So we come back down here. And again, remember how easy it was to calculate these probabilities. A has a probability of a half, B has a probability of a half, and A intersect B has a probability of a quarter. All right, so I'd summarize, we've already done this, of course, but I've summarized these under the next slide. But you can see why, because they're equally likely. Each element, EE, EO, for example, has a probability of a quarter. All right, now, then we plug them into the formula and we did wind up with 3/4. And you can see why, because A has a probability of a half, B has a probability of a half, and A intersect B has a probability of a quarter, which leaves us with 3/4. And we saw that here, you know, the second option of counting them out and coming up with the same result. All right. Now we also started to introduce the simplified version of this rule, which says that if we have 2 events that are mutually exclusive, we don't need to bother subtracting this intersection because that probability is simply 0. All right. So then we jumped ahead and we said, all right, here's a case. Clearly A and B are mutually exclusive. They have no elements in common. So what's the probability of getting either A or B? It's really simple. I'm going to use the simplified addition rule. But first I want to note what these individual probabilities are. Well, clearly, because the sample space has all equally likely events, it should be clear that the probability of A is 1/2 or 2/4, and B is 1/2. The intersection is empty, and so we end up with this result, which means we can use the simplified addition rule. And so let's do it. We add them up, and ta-da, we're done. It just so happens that the probability is 1, and that's because you can see that these cover all the possibilities. In other words, their union is the set containing EE, EO, OE, and OO, which is just the entire sample space. And the probability of the sample space is defined to equal 1. All right, now we still have 2 more rules to look at, so we'll save those for next time. I think we've had enough for one day. So here's what we'll do. The chapter 11, problem set number 2, you're not completely ready to do it just yet, but you can do some of it. So here's what we're going to have to do, because next week is our last class. We'll wrap up this chapter. We'll do the second chapter 11 problem set, and then at long last, we'll do the sample final. And that will cover, of course, chapters 4, 5, and 11. And then we'll be 100% ready for the final. All right. So, wow. Ooh, man. Yeah, the semester has been, it's been a long, long, long semester. All right. So I will see you all next Wednesday. All right. See you then, unless there's last minute questions. Okay. All right. So see you next week.